Hey everyone, and welcome to today's Explainer. What if I told you that every time you bake a cake, strike a match, or honestly, just take a breath, you are triggering microscopic explosions? Pretty wild, right? Well, for all you 7th grade learners out there, get ready, because we're jumping right into Physical Science Unit 3. Specifically, we're looking at Lesson 7, focusing on chemical reaction lab data and CER. That's claim, evidence, and reasoning. We're going to uncover the hidden secrets behind how everyday stuff completely transforms.
So here's our big essential question for this explainer. How can invisible particles explain visible changes in matter? For this one, I want you to think of yourselves as particle detectives. We're on a mission to solve a serious mystery, piecing together clues our eyes can't even see, all to explain the massive transformations happening right in front of us.
And I really do mean all around us. Matter is constantly transforming. Just think about the macroscopic, real-world changes you see all the time. A piece of wood burning up in a campfire, a baking soda volcano bubbling all over your kitchen counter, or maybe an old bicycle chain slowly rusting out in the rain. These aren't magic tricks. It's actually the fundamental rules of the universe in action.
Okay, let's dive right into this. To really grasp these transformations, we need to nail down exactly what a chemical reaction actually is. Simply put, it's a process where the atoms of your original substances are regrouped into entirely new substances with totally different properties. And I want to emphasize that word new because it is absolutely crucial here. The stuff you start with is fundamentally different from the stuff you end up with.
Section 1. Physical versus chemical changes. As particle detectives, our very first clue is understanding that not all visible changes in matter are created equal. Let's break it down. If you take a piece of paper and tear it in half, sure, it looks a little different, but if you zoom in, it's literally still just paper. The molecules themselves haven't changed at all. That is a physical change. But if you take that exact same piece of paper and set it on fire, now you've got a chemical change. It didn't just change its shape, it became entirely new substances, specifically ash and gas. Chemically speaking, that original paper is gone for good.
Section 2. Meet the particle model. To truly understand the chemical change we just looked at, we honestly can't rely on our eyes. We have to zoom way in.
As the next generation science standards framework lays out for us, substances are made from different types of atoms, which combine with one another in various ways. You can think of atoms like the ultimate cosmic Lego bricks. Every single thing you can see, touch, and feel is just a different combination of these tiny, invisible atomic puzzle pieces.
Now, because we obviously can't see atoms with our naked eyes, scientists rely on something called particle models. We use these models to visualize the atomic makeup of molecules, whether we're talking about something simple like ammonia or extended complex structures like table salt. We also use them to predict how particles are going to move. This is especially useful when we add or remove thermal energy, which, as you know, causes a substance to change states, going from a solid to a liquid to a gas.
Section 3. Evidence of a reaction. All right, now that we've got our particle models in mind, let's step into the lab and look at some data. In Lesson 7, a massive focus is that you can't just guess a reaction happened. You have to prove it using CER, claim, evidence, and reasoning. And how do you get that evidence? By testing the properties of your substances. We're talking density, melting point, odor, and flammability. You measure these before they interact, and then you test those exact same properties after. If your lab data clearly shows those properties have changed, boom, you have hard evidence to support your claim that a brand new substance formed.
Beyond that rigorous property testing, there are some pretty obvious macroscopic clues that act as giant red flags for us particle detectives. Say you mix two things together and suddenly feel an unexpected temperature change, like it gets super hot or freezing cold, that's a huge clue. Seeing sudden bubbling, which means gas is being released, clue. A completely unexpected change in color, definitely a clue. These are all vital pieces of evidence you're going to use in your evidence-based discussions to reason that, yep, atoms are actively regrouping.
Section 4. The conservation of matter. Which brings us to a really massive question. When a reaction happens, say you're burning steel wool or mixing zinc with hydrogen chloride, where does it go? Does the original matter just disappear into thin air?
No way! The answer lies in the law of conservation of mass, which tells us the total number of each type of atom is conserved, and therefore the mass does not change. Want to hear a mind-blowing fact? The smoke and ash from a roaring campfire weigh exactly the same as the original wood and oxygen that fueled it in the first place. That's right, matter is never lost, and it is never, ever destroyed.
The rules of regrouping make this super clear. Atoms are not destroyed, and they certainly aren't created out of nothing. During a reaction, the atoms simply detach from one another, rearrange themselves in all the chaos, and then lock back together into completely new molecular structures. It's exactly like taking a Lego castle apart to build a spaceship. If you start with 100 atoms of a specific type, you're going to end with exactly 100 atoms of that type, just built into a new shape. The total mass stays identical.
Section 5. Real-world reactions. So, what does this all mean? Why do these invisible particle rules actually matter to us and to society as a whole?
Well, understanding this is literally the key to modern engineering. By mastering chemical reactions, scientists can take natural resources, the basic raw materials we harvest from nature, and purposefully trigger chemical processes to create synthetic materials. This is exactly how we develop life-saving new medicines, engineer alternative fuels to power our cities, and even create completely new types of foods. We're taking our knowledge of how atoms regroup and applying it to solve real human problems.
Let's look at an awesome transfer task that applies what you've learned, engineering a thermal device. Imagine you're tasked with creating an instant cold pack for sports injuries. First, you've got to select a chemical process, like dissolving ammonium chloride in water. Next, you test it to see if it actually absorbs thermal energy from the environment, which is what makes it feel cold to the touch. Finally, you'd modify the design by tweaking the concentration of the substances to optimize how long it stays cold. You are literally controlling energy by manipulating a chemical reaction. How cool is that?
Which leaves us with this final, incredibly important question. What future problems will you solve by engineering new chemical reactions? Now that you've got the tools to analyze lab data, make solid evidence-based claims, and truly understand how invisible particles rearranged create entirely new materials, well, the possibilities are limitless. Keep investigating, my fellow particle detectives. Thanks so much for joining me for this explainer, and I absolutely can't wait to see what you discover next.